So let us discuss this problem. So the solution for this particular problem is, the very first thing is we have to draw the basin network. So the basin network for this above problem is given like this. The network structure shows that burglary and earthquake is the parent node of the alarm and directly affecting the probabilities of alarm going off. But David and Sophia calls depend on alarm probability. So for this, what we have to do is the conditional distributions for each node are given as conditional probabilities table, or simply we call it as the CPT, as I shown earlier, okay, the diagram, this one. So this is, see here, so burglary and earthquake is the parent node of the alarm and directly affecting the probabilities of alarm going off, and David and Sophia calls depend on alarm probability. So this conditional probabilities table, or simply we call it as the CPT. So already told you that each row in the CPT must be sum to 1 because all the entries in the table represent an exhaustive set of cases for the variable. So when we add these two, that should be equal to 1. That is one condition whenever we are creating a conditional probability table in the Bayesian belief network. And one more thing, in CPT, a Boolean variable with k Boolean parent contains 2 to the power k probabilities. That's why if there are 2 parents, then CPT will contain 4 probability values. So see here we have 2 parents. That's why this particular conditional probability table has become 4 by 4. Okay. So these are the conditions. And very first thing to find the solution of this one is we have to define the variables. First, we need to list of all events occurring in this network. So what are the all events occurring in this network? One is burglary, one is earthquake, alarm, David calls, and Sophia calls. So we need to calculate the probability of the following scenario: that alarm has sounded, but there is no burglary, which is there is no earthquake. Both David and Sophia have called. So A equal to 1, B 0, E 0. And David and Sophia have called, that's why D equal to 1, S equal to 1. So this corresponds to the probability something like this. So probability A equal to 1, B equal to 0, E equal to 0, D equal to 1 and S equal to 1. Now just let us take the observed probability for this burglary and earthquake component. So here already in these values are taken from the conditional probability table. That is probability of B equal to true, which is the probability of there is a burglary is this one, there is no burglary is the value is this one. Probability of minor earthquake is something, this is the value. Probability there is no earthquake occurred is this value. And this is what the table, conditional probability table for alarm A, which we have taken from that one. So just see the values. And then for David calls, this is a CPT, that is conditional probability table. And then this is a conditional probability table for Sophia calls, given there is alarm and there is no alarm. And now from the formula of joint distribution, okay, we can write this problem statement in the form of the probability distribution. So what is the problem? There is an alarm, but there is no burglary, there is no earthquake, but both David and Sophia calls the Harry. So here how we are going to write that one is probability of Sophia and David calls given alarm, there is no burglary, there is no earthquake. So the problem we are going to convert it into a probability distribution, and that how we are going to expand that probability distribution. Just remember, remind us previous this one. Let me show once again. See here how we are going to divide this particular distribution table, how we are in the same way now, okay, probability of x1 given x2 multiplied by probability of x2, like this we are going to solve the same way now for this particular problem statement. Okay. So here, so probability Sophia and David calls, there is an alarm but there is no burglary, there is no earthquake. So it is equal to probability Sophia calls given alarm multiplied by probability David calls given alarm, and probability there is an alarm but there is no burglary and there is no earthquake but there is an alarm, and then multiplied by probability of no burglary multiplied by probability of there is no earthquake. Try to understand this distribution. Sophia called, there is a alarm. David is calling, there is an alarm. And probability there is an alarm, but there is no burglary, there is no earthquake. That is what we have done. And we all, along with that, we should also find out what is the probability there is no burglary, and we should also find out what is the probability there is no earthquake. So now we already know the values from the conditional probability table. So probability of Sophia calls given alarm, probability of Sophia calls given alarm is 0.75. Probability of David calls given alarm is 0.91. Okay. Now probability there is an alarm, but there is no burglary and there is no earthquake. Let us see that value. There is no burglary, there is no alarm, but there is an alarm, but no earthquake, no burglary. It is 0.001. The same value here. Okay. Then probability there is no burglary. Probability there is no burglary is 0.998, and probability there is no earthquake is 0.999. So substitute all these values in the given formula and calculate, multiply these all values, we will get that 0.00068 0.5. That this means there is a 0.066% probability that the alarm sounded without a burglary or earthquake, and both David and Sophia calls the Harry. So this is how we are going to find out the solution with the help of this Bayesian belief network model. So coming to this semantics of Bayesian network, there are two ways to understand the semantics of Bayesian network model, which is to understand the network as a representation of the joint probability distribution. So to understand what is this Bayesian network, first we should be very clear with this joint probability distribution. Why? Because this joint probability distribution helps us to understand how to construct the network. For this, main thing is how to construct the network. To construct that network, we should be aware of this joint probability distribution. And the next one is to understand the network as an encoding of a collection of conditional independent statements. Okay, that is, it is helpful in designing the inference procedure. So we know that inference deriving conclusion from the existing one. So to make that, okay, to understand that network as an encoding of collection of independent statements. So this is all about the Bayesian belief networks. Thank you.